It's Konstantin Zarembo, and he's going to tell us about Hooft loops and integrability. So please, Konstantin.
So I would like to thank the organizers for putting together this meeting and giving me an opportunity to speak. I'll talk about joint work with Charlotte Christensen about at Hooft loops, and our motivation was to study integrability in the context where there is a D-brane in the bulk of ADS space. And there is a kind of interesting interplay between holography, integrability, localization, and S-duality in Hooft loops. So, so the basic setup is this: we consider an object that inserts a brane in the bulk and a string can end on it. And if the boundary conditions do not break integrability, then we can use methods of integrable systems to understand the system in principle exactly and non-perturbatively decoupling. Although what I will talk about is mostly relates to weak coupling. So of course, D-brane can be viewed either as a surface on which open strings end, and then it corresponds to, roughly speaking, to an open spin chain, or it can be considered as a boundary state of the closed string, and this is the point of view I'll mostly take in my talk. So what is the Hooft loop? It is a typical disorder operator. You have some contour in space-time, and the gauge fields have prescribed boundary conditions on that contour. They have a singularity that corresponds to the field of a point-like magnetic monopole moving around this contour. So in n equals 4 super mills, this is the playground where we will be working with. There are also scalar fields, and for supersymmetry reasons, we impose the condition that scalars also have a singularity correlated with that of the gauge fields. So by the Dirac quantization condition, the coefficient in front cannot be arbitrary, it has to be quantized. So all these numbers, so sorry, there's B actually is a matrix, and it can be taken to be diagonal. So by Dirac quantization condition, its entries must be integers. Okay, so this has a well-defined brane model for it, is well-defined. One can consider a stack of D3 branes as usual, but then we can end D1 branes that end on these 3 branes. And so D1 branes correspond to the Hooft line in the world volume of D3. So it defines it defines a defect CFT of codimension 2. So actually, why did I write 2? I don't know. It's actually codimension 3. It breaks part of the symmetry, so obviously translations, for instance. So some supersymmetries, and the symmetry breaking pattern is known. The remaining symmetry form an orthosymplectic group or OSP 4/4. And there are reasons to believe that this, if the Hooft line is a circle or a straight line, the defect CFT is expected to be integrable, which follows from the analysis of string theory of the boundary conditions in the string that was done by Deckel and Oss. So we expect that this will show up signatures of integrability. So our goal was to study what happens at weak coupling. So let me just say a few words of what one means by integrability. When one talking about D-branes, so the string sigma model is integrable by itself, but if we, which means that there are no particle production on the string world sheet. But if we impose boundary conditions that may change, So the boundary conditions will preserve integrability if sending a mode of the string towards the boundary will only result to reflection of this mode with the same momentum. And for instance, the creation of two modes in the reflection process doesn't happen. So if the reflection is elastic, then the boundary conditions preserve integrability. So in the closed string channel, in the closed string channel, this would correspond to, so the debraying corresponds to a state in the Hilbert space of the string. And the state can be, there's a well-defined definition of what it makes for a state to be integrable. It's not an eigenstate of the Hamiltonian, but one can define what it means for a state to preserve integrability. Okay, so we want to probe this setup in some way, and the simplest probe is by correlation functions with local operators. So in the presence of a defect, operators acquire expectation values, one-point functions or condensates. They decay as a power law with the distance from the defect, and the exponent is just the dimension of the operator. This is a simple consequences of scale symmetry. So the coefficient in front is a dynamical number. It's not fixed by symmetry, so it depends on what theory we are looking at, and it contains dynamical information. So in ADS-CFT, in the simplest version of ADS-CFT, that would correspond to exchanging, stretching a bulk-to-boundary propagator between the operator and the d-brane, and integrating over this point of the endpoint that ends on the d-brane. But more generally, the one-point function will be an overlap of the boundary state with the string state that corresponds to an operator. So it's like, so each individual string states, which are eigenfunctions of the string Hamiltonian, correspond to local operators in the gauge theory side. And so we can take this overlap with some boundary state. So in mostly in condensed matter literature, such overlaps are known as G functions or boundary entropy, or yes. So it's basically a partition function with prescribed boundary conditions. So in an integrable theory, this can be efficiently computing using integrability. So there are systematic methods to calculate it using beta ansatz. And it was realized by Jiang, Komatsu, and Vyskovi that the G function, these methods can be applied in ADS-CFT as well. Another important ingredient of that relates to Hooft loops is S-duality. So n = 4 superioring Mills is self-dual under inversions of the coupling. And then electric and magnetic charges interchange, so that a Hooft loop will become a Wilson loop and vice versa. And indeed, one can see that they are parameterized by the same data. So Wilson loop is defined in a particular representation, which we can characterize by its Dynkin labels. That's to say n integers for SUN. The same for the Hooft loop, which are the magnetic charges of basic magnetic charges. So, and they're related in the simple way. So it was realized long back that S-duality gives access to strong coupling for free, in the sense that if you know how to do perturbation theory, compute something at small g, then invert, And then we get an answer that is for a strongly coupled gauge theory. So for radius CFT, it does work, but it doesn't work. And the reason being that S duality doesn't commute with large n. So in principle, even in the holographic setup, we are still dealing with weakly coupled gauge theory. So the gauge coupling is small. So it's the Hooft coupling that becomes large, but that Hooft coupling doesn't transform nicely, or it transforms with a factor of n squared under S duality. So it is only useful if you know the answer completely and exactly. But for Hooft loops, this will be the case. Okay, so how do we set up this calculation in field theory? Well, we can simply do the background field method. Hooft loop is a trajectory of the magnetic monopole, so we just expand around the field of the monopole in the path integral and integrate the fluctuations. So at the leading order, the question reduces to solving the Schrödinger equation for a charged particle in the field of a monopole. And this is a classic problem in mathematical physics. It goes back to the work of Dirac, and it was solved by Tam and Fierz in very, very long ago. So let me briefly describe how it works. So the Hamiltonian is simply the momentum squared, but this is so it's a long momentum. It's a covariant derivative, and so it commutes on the magnetic field of the monopole. But then monopole is, of course, spherically symmetric. So there is one can define angular momentum operator that forms an SU2 algebra and commutes with the Hamiltonian. But notice that it's not just X cross P, it contains also a shift that this actually technically plays an important role. There's a shift that takes care of non-commutativity of the momentum arising due to the magnetic field. So then, once we have an angular momentum that commutes with the Hamiltonian, we can introduce spherical harmonics. So diagonalize L squared and Lz first, and then solve the radial Schrödinger equation. So then one can just go through the algebra, and the spherical harmonics in the field of the monopole, they can be constructed explicitly. So the angular dependence is just an exponential, and then there is a function of theta that satisfies some differential equation. Notice that periodicity of the wave function is actually equivalent to the Dirac quantization condition, because this should be a multiple of 2 pi, but then m, which is the magnetic quantum number, better be an integer for SU2 representation theory. From that, we infer that B over 2, the magnetic charge, half of the magnetic charge must be also an integer. But okay, so if you look at this differential equation that describes the spherical harmonics, one can continue sort of switch on the magnetic field of the monopole adiabatically, and then this equation describes the spectral flow. So first we start with the usual spherical harmonics. They form SU2 representations as the usual triangular structure of SU2 multiplets. If we switch on infinitesimal magnetic field, this picture completely destroys. So some of the levels move up and to the left in the magnetic quantum number. Some move to the right or actually they all move to the left, but some of them move down and some move up. So the multiplets essentially get destroyed for the field, for the field that is infinitesimally small. But they move diagonally, and at some point, they miraculously recombine into full SU2 multiplets. And that happens precisely when the Dirac quantization condition applies. So the first time it happens when the magnetic charge is 1/2. And then the harmonics are half integer. So we started with a particle that was a boson, so it's with integer angular momentum, for instance, spin 0. But then in the field of the monopole, its orbital momentum will be half integer. So monopole fractionalizes angular momentum and actually statistics as well. So here is an example of how the multiplets look for magnetic charge 1. And so here this spectral flow goes 1/2 step further. And in particular, it removes the angular momentum here is again integer, but there is no spin 0 state. And in general, the spin is quantized, well, in integer, half integer units, but starting with the magnetic charge of the monopole. So in field theory, expansion in the spherical harmonics is the same as going to the anti-de Sitter coordinates in space-time. So we can write flat metric as R² times the metric of ADS2 cross S2. And since we are dealing with the CFT, the overall conformal factor will drop out. So in a sense, we can think of a defect CFT as a CFT defined on ADS2, and then, well, there is also S2, but we can do Kaluza-Klein reduction. And that's precisely the expansion in monopole harmonics. So at the end, we will have infinitely many fields on ADS with masses that are quantized as prescribed by SU2 representation theory, but also the angular momentum starts with the charge of the monopole. So the IDS dictionary also relates them to scaling dimensions. And I mean, it's the scaling dimension turns out to be the angular momentum +1. And physically, this quantum numbers describe various operators that can be inserted in that Hooft loop. So, they, to the leading order in perturbation theory, they have dimensions B over 2 + 1, B over 2 + 2, etc. So in principle, well, this picture will get quantum corrections. In particular, if you want to compute a one-point function, the zeroth order approximation will be just substituting the classical field of the monopole inside the operator. Then we can connect two fields by a propagator, and then the rest will be saturated by the classical field, and so on. So I'll give an example of this calculation later, but to have a wrapper point, it's useful to have some prediction. And one can get such from localization. So if we consider a circular Hooft loop, then it is dual to circular Wilson loop. So one can combine localization results for circular Wilson loop with this duality and get predictions for the expectation value of that Hooft loop and for its correlators with the local operators. This can be also done directly. One can do localization directly for the Hooft loop. So let me remind you how it works for the Wilson loop. So one can compute it exactly so this formula is non-perturbative, both coupling constant and n. And then if you take n large, then this becomes just some function of lambda, which at strong coupling exponentiates, and the exponent agrees with the minimal area law in anti-de Sitter space. But at weak coupling, it has the usual perturbative expansion. So we just take this formula and apply invert the coupling constant. But this is, we need to invert g squared, not lambda, or if you invert lambda, there is an extra factor of n squared. So the large n limit has to be taken anew. We cannot take the large n limit and apply as duality. That's would give a wrong answer. And so the large n limit actually is completely different. So at Hooft loop exponentiates at any coupling. If you take n large, then we get a large exponential with of order n times some function of lambda. So if lambda is small, this function is actually very large. It's inversely proportional to lambda plus some logarithmic corrections and plus power series in lambda. And that's precisely what one would expect from perturbation theory. So the leading order is actually the action of the Dirac monopole. And logarithmic correction comes from the one loop determinant from zero modes that arise for various fields. Also at strong coupling, one can match it with ADS CFT, so one can compute this function exactly, of course, but then at large lambda, it goes as 1/square root of lambda. And this matches with the tension of the one brane that is dual to the Hooft line. So the tension of the D1 brane is 2n divided by square root of lambda. That one multiplies by 2 pi, which is the area of the minimal surface. And one gets precisely the right exponential that agrees with localization. So one can do the same for the correlator, for the one-point function, the correlator of a local operator with the Hooft line. Again, there is an exact answer for the Wilson loop, which now is a sum of some various Laguerre polynomials of the coupling constant. One then can S-dualize, take the large n limit, and short calculation shows that that the result is given by this nice formula. So one can, of course, compare it with supergravity and with perturbation theory. I'll shortly describe how it works, but it also has a nice interpretation that points towards possible integrability origin of this formula. So in integrability, one typically introduces Zhukovsky variables. They parameterize the kinematics of the integrable system of ADS CFT. So there are some special points in the Zhukovsky plane, namely half-integer points along the imaginary axis are, in many reasons, special. So one can introduce just numbers xa, which are functions of lambda. And what is written here can actually be expressed in simple ways in terms of the Zhukovsky variable x1. So in other cases where one can apply similar techniques, namely for D3, D5 system that describes a domain wall in n equal 4 Young Mills, a very similar formula was derived by Komatsu and Wong, but it was substantially more complicated. So it consisted of a finite sum of positive powers of x with various indices, and then an infinite series in 1 over x. And there it was found that each term with the positive power of x corresponds to a bound state of an elementary Magnum scattering of the d-brane. And the inverse powers correspond to wrapping corrections. And we expect the same to be true here, but you see that there is only one term, meaning that magnums will not form bound states. And also wrapping corrections are super simple, so they only consist of one term. And I guess this simplicity just asks for more mathematical explanation. But so far, well, the best we can do is check this formula perturbatively at weak and at strong coupling. So at weak coupling, if one expands this result in lambda, what one gets is something that's proportional to, well, at the one loop level, the answer is proportional to L, the length of the operator. And this is precisely what perturbation theory would produce, because these propagators can connect in pairs, and only nearest neighbors give a non-zero result. And there are precisely L pairs of nearest neighbors. So if one goes through this long calculation with spherical harmonics, etc., does Kaloutsky-Klein reduction in ADS2, so eventually one produces also the prefactor. I want to emphasize that this number is very simple, but to obtain it, one needs to really work hard. It's a result of summing over the infinite tower of Kaloutsky-Klein modes on ADS. So on the string side, one can also do the same calculation of the same object. So for that, one needs to stretch a propagator in the bulk and integrate it over the brane with the weight that's basically the vertex operator of of the mode that describes coupling of this mode to the world sheet. So this integral can be done, and it also gives the result that agrees with localization. So there is another limit one can take, and this is basically the Bman limit when we take both the coupling large, but also the charge, the R charge of the operator to be large. So localization then predicts an answer that depends on the coupling or depends on the Bman coupling. And it looks like, it looks indeed as a one loop determinant, so this can be written as an infinite product over energies of Bman modes. Unfortunately, I don't know how to make like a more precise sense. How can it be related to partition function of the string, for instance? This so localization, of course, can only compute protected quantities that preserve some part of supersymmetry. But if we believe that this that Hooft loop preserves integrability, then we should be able to calculate also non-protected one-point functions. And this is what I will describe in the rest of the talk. So we start with a more general operator. For instance, we can consider operators that are built of just scalar fields in the SO6 sector. They are described, so they mix, and their mixing is described by an integrable SO6 spin chain. It can be efficiently diagonalized using beta ansatz. So let's see what happens if one inserts such an operator in the background of that Hooft loop. Then to the leading order, one just needs to substitute classical fields for each entry. So the operator is a product of fields with some contracted with some tensor, which is the wave function of the spin chain. So one needs to substitute a given value, which is well, some diagonal matrix for each of the fields. And we are considering the simplest case where there is only one non-zero entry in this diagonal matrix, and moreover take it to be equal, the magnetic charge to be equal to 1 or to 1/2. So then what happens is that we need to pick up a particular component of the operator's wave function. So we project this tensor on a particular direction in the flavor space, dictated by the direction in which we place the D-brane, or well, which direction in which the in our symmetry space where the classical field points. So in other words, what we get is an overlap formula. The one-point function is an overlap of the physical state describing the operator on some given boundary state that in this case is a very simple tensor, which is tensor product of some unit vector in some direction. So simple as it is, this boundary state has remarkable properties. It is actually integrable in some sense. Let me describe what it means to be, for a boundary state to be integrable. So the system is solvable by beta ansatz, which is a set of equations on Magnon rapidities. So one needs to solve a set of beta equations, and then the anomalous dimension can be computed from them algebraically. And in principle, the beta roots, the rapidities of magnons, can be arbitrary complex numbers only constrained by these equations. There are as many operators as solutions to the beta equations. So what integrability means is that only solutions that are invariant under parity correspond to non-zero overlaps. And this is a very strong statement, actually. It means that the states, so the magnons on the spin chain should be always paired. So if you have a magnon moving left, there should be the same equivalent magnon moving to the right with the same rapidity. So not that all states are such, obviously, but the claim is that the boundary state that we found from the Hooft loop only projects onto the states that are invariant under parity. So this is actually what is usually taken as a definition of integrable boundary state, and it has to do with the sort of cross-channel picture where magnons reflect from the boundary. But just technically, it also means that we can compute the overlap algebraically once we know the solution to the beta ansatz equations. Well, for this state, the overlap formula was actually known, was derived by the Leofeld collaborators. But all these overlap formulas always have the same structure. So they are given by the ratio of, actually, this ratio can be regarded as a superdeterminant of a matrix that's basically the Jacobian of the beta ansatz equation. So one differentiates the log of the beta equations in rapidities. That produces a matrix. And since we consider only states that are invariant under parity. There is Z2 symmetry in the problem. Regarding this Z2 symmetry as fermionic symmetry, we can form a superdeterminant. And then it is dressed by some products of simple products by beta roots. So such overlap formulas are known in the literature for many, for some specific but different states and various quantum speed chains. And they always have the same form, with the only difference being what stands as a prefactor, which products of beta roots appear. So to conclude, the one-point function is given by this algebraic form, and one doesn't need to diagonalize the Hamiltonian. Just solving beta equations and then plugging into this formula is enough. So another example is SL2 sector. So one can consider operators that contain derivatives, that are built of one type of scalar fields, and then we differentiate each of these fields arbitrary number of times along some light cone direction. D plus is a light cone derivative. So these operators only mix among themselves, and their scaling dimensions can be computed by beta-ansatz equations. In that case, there is only one equation to solve. One can see what happens if we plug in the monopole field for the scalars. So the monopole field is basically is going as 1 over r. So when we apply a light cone derivative, and here only the spatial part is important, to 1 over r, the result will be proportional to the Legendre polynomial of nth degree. So the boundary state is again a tensor product state, but each element in the tensor product has a very specific form. It is a sum of states with n derivatives weighted with Legendre polynomials. And this state turns out to be integrable, and it's important that these functions are not arbitrary, but are given by Legendre polynomials. So there's only one, it's not one state, but one parameter series of states. Actually, they simplify along the light cone. If you consider placing the operator in the same direction in which we take the covariant derivatives, then the state is actually a descendant. So Legendre polynomials disappear. And so this state can be generated by acting with derivatives. It's basically a shift operator acting on the vacuum. And so the dual to it, which is the boundary state of interest, is created by the conformal spin. And conformal spin annihilates any primary operator. So from this, we conclude that on the axis, on the z-axis, if you place a primary operator on the z-axis, then its one-point function will be 0. So this is sort of a simple symmetry check, but one can also derive a formula for the overlap, and the way we arrived at it is we just guessed that this formula should describe the one-point function. So the formula is complicated, but it's not as complicated as it looks. The only thing to guess here is the ratio of the Q functions, and that can be easily found by considering simple states, for instance, with 2 magnons. And then we check that this works on a couple of hundreds of states. So this formula describes a one-point function of arbitrary SL2 operator. Now, in principle, there should be a general formula that describes all possible operators, and not only at one loop, but that requires more work. And in principle, there is a well-defined procedure to obtain a non-perturbative answer by studying reflection of magnets of the brain. So, so our results just points towards the existence of this non-perturbative framework. But so far, they're only available at the leading order of perturbation theory. So thank you very much. This is all of what I wanted to say.
Yeah, thanks very much for this very clear talk, Kostya. So I'm sure there's questions. Yeah, wait, let me review.
Yes.
Anybody else?
The expressions for when you insert the chiral operator, they are exact in lambda and n. So is there a way in which you can test a 1/n correction in the strong coupling limit by
You mean for localization?
Yeah, so the 1-point function between these Laguerre's expressions that you said, they are exact in...
It's like these ones.
Yes.
Yes, so they're exact. I don't know how to 1/n. I'm not so sure. Do you know if this has been done for Wilson loops?
No, it hasn't been for Wilson loops either. So, but that's.
Yes, 1/n corrections I think are in general hard, but there are recent results, for instance, by Jomby and Saitlin, that they mostly discuss expectation values, I suppose. So presumably, what their methods can be also applied to Wilson to D-branes, to Hooft loops.
Okay, thank you.
More questions?
Correctly, this discussion is for large L, or is it also for small L?
So this formula is non-perturbative in all parameters. And
your integrability formulas.
Integrability formulas are also applied to any lengths. This formula is exact for any lengths, but it is one loop formula, so it is leading order in the coupling constant.
Ah, okay.
More questions?
Not for this. You mean integrability formulas? Yeah, not in this case, but in very similar setups. For instance, for for D5 brane and for giant graviton in ADS, the exact formulas are known. So for D1 brane, they're not known, but they have to be of the same type. So it's just a question of how to decorate this. So that there's some basic structure, which is ratio of determinants or Fred-Holm determinants, but they're decorated by some Q functions, and that is model specific. So that details are not known.
And one of these determinants, is it the Godin determinant, or?
So this whole ratio can be regarded as super determinant of the Godin matrix. So you take Godin matrix. Because of this reflection symmetry, there is Z2 transformations that act on it in a natural way. So once you have Z2, you can define a superdeterminant of a matrix. And this is this ratio. But it's the same Godin matrix that enters the norm.
And are there SOV formulas for this ratio?
I think so. Yes, I think there are integral representations for this ratio, which basically should be equivalent to SOV formulas. But for the norm, so SOV works nicely when you can introduce a twist. So this story with the boundary states, it does not allow for twist to enter, because twist would immediately destroy this parity invariance. So the answer is yes and no. I mean, there are no integral representations which look like SOV, but SOV derivation is not available.
So are there further examples for integrable DCFTs, maybe also Koda mentioned too?
There are various examples of various codimensions. There is a classification for integrable D-branes by Deckel and Oss. It's also known to be non-exhaustive, so there are more examples. But yes, there are many examples of integrable D-branes.
Yeah, thanks. Anything else? Well, if not, let's thank Costa again for the very nice talk. So I understand now there's the workshop photograph, and we convene at 11:15, but let me pass to